Thank you to the Academy for selecting me and giving me this opportunity to present my work. Sorry, I've had a cold. Coming from Bombay, I did not anticipate Bhopal would be like 15 degrees in the morning. Okay, all right. So what I'll talk about is a theme that has sort of emerged through our efforts in the recent past, about the last 4 or 5 years. And that the theme is that we are developing, we are forming now what I call a convex-analytic view of certain impossibility results in stochastic control. I'll clarify what all of these terms mean. The story begins with this setup. This is what Shannon tackled in his pivotal paper in 1944 called Mathematical Theory of Communication. So you have a source which is, say, some messages 1 to m, which have to be sent across over a noisy medium to a destination. Okay, the destination, the source is going to be some s from this set. The destination will get an s hat from this set. What we want to do is make this happen with as little error as possible. So in the pre-Shannon era, this naive approach was to simply encode. So the noisy medium here is what is called a channel. So in the sense, if you send in, say, a symbol either 0 or 1 through this, what you will get is a y with a certain probability, which is also 0 or 1, but you will get a different y with a different probability. The naive approach was to just naively encode and simply send each message multiple times, average out what the output is, and then thereby decode. This is what one would have sort of naively done in the pre-Shannon era. What Shannon does is he introduces a number of novel ideas. The core idea is what is called block coding, which is I'll explain that later. He encodes symbols with redundancy, so he doesn't do naive encoding, and then he encodes them so that the noise in the channel can be defeated, and then the decoding can be done at the other end. Okay, so Shannon looks at basically this setup. So you have a source which takes values, say something from 1 to m messages. He encodes them as a string of symbols, x1 to xn. Okay, that string passes through the channel. Each xi emerges as a yi. Then that entire string is en masse decoded, and you decide what was sent. Okay. Now, so this is called the block coding setup. So you have this block of symbols and a block of symbols here. So essentially what you have here is a function that maps each of these symbols to a string of inputs. Okay. So and what you are concerned about is these quantities. You are concerned about the probability of error. Now the probability of error will depend on the choice of these functions, so the encoding and decoding functions. And it depends on how many messages you had to send and how long of a string did you choose, how big of a block did you choose. So generally the normalization done is that you take m to be some 2 raised to nr, okay, and where n is the length of your block. R is so you fix r as a parameter. So you look at the probability of error as a function of the code, the parameter r, and the length. The probability is just the probability that s is not equal to s. That's your probability of error, right? And what you would want is this, which is p of r comma n, which is the smallest probability of error over all possible codes. Okay. Now, quick calculation reveals that there are a humongous number of codes. Okay, so this, even for a small block, even for like a block length of 5 or something, the number of codes is huge. Now, what Shannon showed was that this problem, which seems almost impossibly complex, has an extremely simple solution. And that solution is this graph. So if he shows that there is a quantity c, which can be pre-computed, c, which is given by some formula. We don't need to bother why that formula comes up, but essentially there is such a quantity which you need to know, which you can pre-compute, and with the following property, that if r here is less than c, then this probability of error can be driven down to 0. So essentially as n goes to infinity, the probability of error becomes 0. So you have completely reliable communication. And if r is greater than c, then the probability of error is 1. Which means that any code is unreliable. There is no reliable code. Any code is as unreliable as possible. Okay. So notice that here there exists a code, that means there is a sequence of codes which will bring the probability of error down, and this is for all codes. Okay. So this result and several other results in this paper basically set the taste for this field. Essentially, what he showed was there is a problem that looks impossibly complex to begin with, can be brought down to a simple quantity like this, and you can express the truth of this problem through just not the knowing of that one simple quantity, which is this quantity C. That quantity was called channel capacity. There are analogous other quantities for other types of problems. Okay, so this drop in complexity is what defines the sort of nature of results people look for in this field today. Okay, and that sort of has its moorings in Shannon's original work. Okay, so now, but that leaves some open questions. Okay, when something so elegant works out, it leaves out some open questions. So first is, of course, what about finite block length performance? Because this is the limit as n tends to infinity. So this is a mathematical limit. An engineer would want to say, would fix a particular block length, a particular R, and ask, okay, what is the probability of error? Can you tell me? Okay, so that is something he would want to know. So that's finite block length performance. Okay. Now it turns out this because of the number of codes involved is even computationally very hard to do, and it's extremely hard to compute even as n goes large. Even for moderately sized n, to be honest. Okay. Then there is a mathematical question of why does this happen? I mean, how does this something that is so complicated at a finite block length level, impossible, very hard to compute, takes longer than the age of the universe to compute even for moderately sized block length, becomes so neat and tractable once you take the limit. So there's something that is happening here. And then what about networks? So this setup was that I described was when there was one source to be sent over to a destination. What if you have something more complicated? Say suppose you have a source here, that they are both sent into the channel. The channel spits out some sort of some jumbles them and throws out a y, and at the destination you have to sort of unravel them and decide what was actually sent. Or you have a very general network, this could be a whole bunch of cells all signaling through a sequence of sort of transmissions between each other, and at the end you want to come out with some sort of, say this is often sort of way people try to think of as say happening in the brain, that you have a lot of cells receiving signals from the outside, and you want to find eventually at an abstract level in the brain, you want to see if what you're observing, is that a scenery, is that day, is that night, etc. Okay, so then there is a question that is internal to the field, which is that Shannon the way Shannon proved all this, which is that he invented a calculus of something called mutual information. So he invented a way by which you can almost do all this in a dumb manner, without knowing much about what's going on at the sort of at the substrate level. So he invented a calculus that just let you do some calculations from which all of these theorems sort of start following. Now this calculus works for problems which are of this nature, where you are looking for, where probability of error is defined as probability of that S is not equal to S hat. But if you change this slightly, so if you say, for example, I want probability that say something here is not equal to something here. Okay, so you're interested in some other metric for whatever reason. Then that calculus fails, and nothing actually works. So there's this delicate little thing that seems to succeed, and and we don't quite know why. And it's not fair to say we don't know anything about it, but we do not know very well why all of this works in this specific setting. Okay, and so therefore that leaves question of proofs, generalizations, and so on. So, okay. So now my this thing here is interest is in the lower bounds part of it. So we want to know how this happens. Okay. As far as this is concerned, people have been able to do this by basically very ingenious code constructions. That's not my focus. My focus isn't getting to here. So that means I want to show that to show impossibility results. That there can be there is no code that will assure you less than 1 probability of error and those sort of results. So now the existing approach that has been taken is basically this is a problem in probability. So one approaches it directly through probability. So that's been the approach. So our approach has been different in that we look at the convex analytic geometry of the finite block of the problem. Okay, so this is okay. We are able to get some good understanding about the geometry of the problem, then approximate that geometry using a bunch of hyperplanes, and then from there we were able to derive results that people had derive and improve on results that people had derived by appealing only to probability. So this is the overall story. I will explain more in detail. Okay. So when I show her photo, it often looks like this is an ad for a shampoo or something like that. This is my student. Okay, my student Sharu is so this is she's a number of these the results that I'll talk about are actually attributed to her. Here's the basic idea. We have an original problem here, which is extremely complicated. What we can now this problem actually is a discrete optimization problem over a vast number of codes. We can show that it's equivalent actually to a problem over distributions, over probability distributions. And in this space, it turns out to be we can show that it's necessarily a non-convex problem. Now from there we go to a convex we create a convex relaxation of this problem, and then from there a particular relaxation is the one that I mentioned, where we approximate the geometry of the problem with a number of hyperplanes. Now from this we get to essentially this schema for deriving bounds. So you have the information theory problem that is lower bounded by the problem with, so this problem where we have approximated the geometry with hyperplanes is actually a linear programming problem. So that basically gives us that the information theory problem is lower bounded by a linear program, and then by linear programming duality we get that the value of any dual feasible point is a lower bound on this. So essentially, linear programs have this property that they come in pairs. You have a linear program and then you have its dual, and in very general settings you have the following equality, that the linear program and its dual their values are equal, and the value of any feasible dual point is always less than equal to the value of this dual. So essentially, this now yields us a suite of lower bounds by just varying the choice of the dual point. None of this uses any probabilistic techniques as yet. This is all appealing completely to the geometry of the problem. Okay, so it gives us a suite of lower bounds, and this chain here, going from here to here, here to here, here to here, all of this generalizes also to network settings. So we do not need the calculus of mutual information or any of that so far. So the question now is, how good is this? What is the test? So it turns out all of these results can be recovered from this. Okay, so we get asymptotically tight finite block length lower bounds for channel coding, for the channel coding problem that I mentioned, for source coding, for joint source channel coding. These are the sort of the canonical information theory problems. All of those can be addressed. Moreover, we get improvements over previous bounds. Okay, so I have not stated any formal theorem as yet, but here is, for example, one theorem. Okay, so if you consider a discrete memory as something called as a binary symmetric channel, so that is when the 0 goes to a 1 with probability epsilon and the 1 goes to a 0 with probability epsilon, then we can show that for any code the probability of error is at least this expression here. Okay, where certain things can be defined here. Now how is this different from what we knew before? From what we knew before, we can come to this sort of an expression where you have 1 minus these sort of terms. These are all negative terms. So 1 minus all these terms. But we get we get 1 plus something positive minus this. So we get a stronger lower bound. Okay. Now, not only that, we can do this for networks. You get scarier expressions. It shouldn't be mentioned in in a talk like this. But anyway, this is just evidence that there's some research actually going on. So now, since there are just a couple of minutes left, let me just mention this. So what this idea of what have we done actually? So we've taken a problem, written a stochastic problem, written it as and looked at probability not as probability itself, or rather looked at probability not as a measure, but rather as a vector. And when you look at it as a vector, it has a geometry. Okay, once you look at it as a vector, it has its geometry. In the simplest sense, where does the probability vector lie? It lies in a simplex. But if it's a joint distribution on certain variables which are, say, conditionally independent of each other and so on, that conditional independence induces a certain geometry and some constraints on where that probability vector can lie. We have attacked that geometry, and from there we are being able to produce results that one would otherwise get by appealing to the measure theoretic. So now this idea of writing a problem on distributions has been done before. Borkar and so on have done this for the case of Markov decision processes. Now, if you apply, now what happens there is you directly there get a linear program. You do not need a linear programming relaxation. So our results, in some sense, unify MDPs with stochastic control and information theory. Through these arguments, we were able to, this is an older work of mine, where I was able to sort of answer some key questions about the role of Shannon theory in stochastic decentralized control. In a similar vein, we had also tackled an open problem posed by Liebenstein on the deletion channel. This is a combinatorial open problem. Liebenstein had basically shown that the largest zero error code for a deletion channel of block length n had a size at least 2 raised to n by n plus 1. What I had shown was this. You can get a very that code is in fact very so he got this lower bound through a code construction, and what I can show is that construction is actually quite good. Okay. So essentially, looking forward, what we have is what we are getting to is basically a convex-analytic way of arriving at fundamentally probabilistic results, and through the geometry of probability. And so this is just the beginning. As I said, just 4 or 5 years of work, and many more results should be pouring out from here. Okay. So just quick acknowledgements: DST, IRCC. Kaliyappan is here, who was the Dean of R&D when this project was granted. So thank you.
And I thank you for your attention.